we'll consider about projection of velocity. So as we consider a circle as a reference circle, with center at origin O, like initially the particle will be present at position A, so the initial phase over here will consider as phi. From A with uniform angular velocity, say omega, if the particle moves for the time t, then it reaches the point B. So this angle becomes omega t. Now, this will be the displacement of the particle with respect to the mean position. Now, at this particular point, if v is the velocity, that is the instantaneous velocity v in the particle, or the velocity v is acting on the particle so that it is moving on the circumference of the circle, then we can resolve this velocity v into two components. So, there will be a velocity which will act toward the y-axis and the velocity which will act along the y-axis. And so, resolving this angle becomes equal to the angle theta, where theta is equal to omega t plus phi. So this will be v cos of theta, and this component will be v sin theta. So v cos theta is the velocity which takes the particle along the y-axis so as to perform the projector as simple harmonic motion. And so velocity in the simple harmonic motion will be v cos of theta. So v cos theta can be expressed as v cos of omega t plus phi. But in uniform circular motion, what we consider about the velocity is, if a is the radius of the circle, then v will be equal to a omega. And so if we put the value over here, then the velocity, the projection of the velocity as a SHM becomes equal to a omega cos of omega t plus phi. And so this becomes the expression for the velocity in simple harmonic motion. Yes. Now, as we consider the velocity as a omega cos of omega t plus phi, acceleration in simple harmonic motion is dv upon dt. Means this will be d of dt of a omega cos of omega t plus phi. So this is what we call as the projection of the acceleration in SHM. A omega is the constant term. Derivative of cos will be minus sine of omega t plus phi into derivative of omega t plus phi with respect to t will be omega, and so acceleration will be minus a omega square sine of omega t plus phi. So we can express this as minus omega square into a sine of omega t plus phi. But this is nothing but the displacement in SHM, and so acceleration will be equal to minus omega square y. When we take the same relationship along x-axis, the acceleration is given as minus omega square x. Depends upon how we are taking the path of the SHM. And so in the previous lecture, when we were studying about the differential equation, say, now here the acceleration in the simple harmonic motion is minus omega square x. And there in the previous case we have derived the expression as acceleration is minus k upon m x, and so k upon m in that case for a differential equation we substituted as omega square, where omega is angular velocity with which the particle moves on the circumference of the circle. And so now when we consider about the projection of the phases in SHM, the general expression as we have taken as y is equal to a sine of omega t plus phi if the SHM is taken along the y-axis, or the expression can be written as x is equal to a sine of omega t plus phi if the SHM, the path of SHM is taken along the x-axis, whatever it may be. Now considering the first expression, if we see the particle on the circumference of the circle is on the x-axis, then its projection will be at origin. So the particle which is going to perform simple harmonic motion will be on mean position. Yes, at that time the angle with respect to x-axis is 0. So initial phase is 0. Angle itself, omega t, is 0, and so the particle is at mean position. And so expression is written as y is equal to a sine of omega t. This is the condition when the particle initially is present on the x-axis. And then the circular motion will begin, so that the projection on the y-axis, the displacement will go on inversely. With the start of the SHM, if the particle is on the y-axis over here, then the initial angle phi will be pi by 2. And so, for a particle which is present at one of the extremity, positive extremity, and then if the SHM is going to begin, then the expression becomes y is equal to a sine of omega t plus pi by 2 means this becomes equal to y is equal to a cos of omega t. And so if the SHM is going to begin from one of the extremities, a positive extremity, then the expression for the displacement is y is equal to a cos of omega. Here the phase is omega t plus pi by 2, initial phase is pi by 2. If initially the particle lie on the x-axis, but the angle is pi. Sure, the particle will be on origin, but it will be on the verge of moving toward the negative direction. Yes. Initially, when particle is at x-axis on the right hand side, the particle tends to move in the upper side. Its displacement is on the upper side. When the phase becomes omega t plus pi, now the particle, its projection is on origin and the displacement, the direction is in downward direction. And so, when it becomes 3 pi by 2, the expression comes that particle will start its SHM from the other extremity, from negative extremity. The expression becomes y is equal to minus a cos of omega t. And after 360 degrees, the particle is at the same position, omega t plus 2 pi, which is omega t itself. Sine of omega t plus 2 pi will be sine of omega t. So, original position. And then as the particle moves on the circumference of the circle, its projection is going to perform simple harmonic motion. So in this way, we have considered the field. This has been applicable to when the SHM is along the x-axis also. Now we'll study about the composition of two SHMs. The concept of composition of two SHMs is, for example, if the particle is performing SHM along the path AB on its axis, O is the mean position, now, we are considering the two SHMs. So, in SHM 1, the particle which is performing simple harmonic motion, let the amplitude be A1. And let the initial phase from where the particle is going to begin be phi1. And so in this case, the equation of displacement of the first SHM be x1 equal to a1 sine of omega t plus phi. Yes. Now in this case, the particle will be somewhere over here and its displacement is given as x1, or otherwise we will consider the position somewhere over as x1. Now consider another path. which is CD. The path CD is over the path AB itself. They are collinear to each other. Now, for the path CD, if the particle is going to perform simple harmonic motion, then the amplitude of the second SHM, let it be A2. And initially, the particle will be at say another position where its initial phase will be phi2. And so, for the second SHM, the displacement of the particle in its initial form will be given as x2 is equal to A2 sine of omega t plus phi2. Now here we are having the two expressions of the displacements. x1 is equal to a1 sine of omega t plus phi1, x2 is equal to a2 sine of omega t plus phi2. Now suppose if these two SHMs are applied to a single particle, means it has to perform both the SHMs simultaneously, then its displacement will be the resultant of the two displacements. It will be the vector addition of the two displacements. And so the combined displacement of the two SHMs together, it will be x is equal to x1 plus x2. The combined displacement when the two SHMs are on the same path but having the different amplitudes and different initial phases, but the single particle has to undergo the two SHMs simultaneously, and then the resultant of the two will be x is equal to x1 plus x2. And so the resultant equation for the given displacement x will be a1 sine of omega t plus phi1 plus a2 sine of omega t plus phi1. So this will be the combined equation of two SHMs. And so particle, say, if this is the x2 displacement, if this is x1 displacement, then the combined effect of this x1 and x2 particle will be at some different position, and that different position is the resultant position, that is x. And so this is the expression x is equal to a sine of omega t plus phi1 plus a2 sine of omega t plus phi2. If we solve these two expressions, then we are able to give the combined equation. Yes. So, in order to solve this particular expression, we will be using the formula sine of a plus b, that is sine of a cos of b plus cos of a sine of b. This will be our formula to expand this relationship as well as this relationship. As x is equal to a1 into bracket, this will be sine omega t cos of phi1 plus cos omega t sin